This journey of learning about quadrilaterals has been so fulfilling, right? The last couple of videos have taught us so much about parallelograms. We have learned how a diagonal of a parallelogram divides it into two congruent triangles, and how the opposite sides and even the opposite angles are equal. Just a couple more properties to go and you will become a true master of this shape called a parallelogram. So, can you guess what these properties are about? Some other sides, angles, or diagonals? Put on your seatbelts and get ready to find out. We know that if we take a parallelogram, say A, B, C, D, and then join each of the two pairs of its non-adjacent vertices, we would get the two diagonals, namely AC and BD. And we also know that each of these diagonals divides the parent parallelogram into two congruent triangles. But is that all we need to know about these diagonals? Or there's more to them than what meets the eye? Let's stop speculating and just measure them to find out. So, on measuring with a ruler, we see that AC is 20 centimeters long. Funny how this point where the two diagonals meet, say O, seems to be the midpoint of this diagonal AC. So let's just use the ruler to confirm. Voila! OA actually measures 10 centimeters. This means that OC will also measure 10 centimeters. They really are equal. Diagonal BD seems to be bisecting diagonal AC. But what about AC? Don't you think AC is also bisecting BD? Seems quite like it, right? On measuring with the ruler, we see that BD actually measures 14 centimeters and OB and OD each measure 7 centimeters. They are also equal. Diagonal AC is bisecting diagonal BD here. This enables us to say that in this parallelogram, the diagonals are bisecting each other. Let's try the same with another parallelogram, say this one. So, on measuring the diagonals and then looking for the midpoint of each diagonal, we see that the midpoints coincide. It's evident then that the diagonals are bisecting each other. Now, you can try the same with parallelograms of different shapes and sizes. But each time you will arrive at the same conclusion. The diagonals bisect each other. So this brings us to the fourth property of a parallelogram. The diagonals of a parallelogram bisect each other. Now, a rectangle is also a parallelogram, right? So on measuring the diagonals and then checking for the midpoints, we see that here too the diagonals bisect each other. Additionally, the diagonals are also equal. This is in fact a differentiating factor between rectangles and general parallelograms. We see that in a general parallelogram, the diagonals bisect each other, but they are not equal. However, in a rectangle, the diagonals are equal and they bisect each other. Now, since a square is also a rectangle, doesn't it mean that here too the diagonals are equal and they are bisecting each other? Well, on measuring with a ruler, we see that they really are. So it's safe to say that the diagonals of any parallelogram bisect each other. So now that we know the property, what's the next logical step? Proving it mathematically, right? So without further ado, let's get on with it right away. Here's a parallelogram ABCD where the diagonals AC and BD meet at O. Now, in order to prove that this theorem holds true, we just need to show that O is the midpoint of each of these diagonals. Or in other words, OA is equal to OC and OB is equal to OD. Now this is pretty simple. All we need to show is that these two triangles are congruent. So each of these pairs of sides are equal because they are just corresponding parts of congruent triangles. So now let's just see the steps. If you think about it, the diagonals AC and BD act as transversals between each of these pairs of parallel lines. So this angle would be equal to this angle because they form a pair of alternate interior angles. Similarly, this angle would be equal to this angle because they too form a pair of alternate interior angles. For ease of understanding, let's just name them 1, 2, 3 and 4. So, in triangles AOB and COD, angle 1 is equal to angle 3 and angle 2 is equal to angle 4 because they form pairs of alternate interior angles. Now, AB is equal to CD because they are opposite sides, and by the second property, the opposite sides of a parallelogram are equal. So, angle, side, angle. Thus, triangles AOB and COD are congruent by the ASA criterion. Then, OA is equal to OC and OB is equal to OD because they are corresponding parts of congruent triangles. This just helps us conclude that the diagonals of a parallelogram bisect each other. Wasn't it pretty easy to prove? I told you, I am so proud that these concepts are coming to you naturally. A lot of it is the outcome of the approach we have been employing to prove the theorems and the converses so far. Talking about converses, what do you think would be the converse of this theorem? We just have to switch the given part and the proved part, right? So, this theorem basically tells us that if a quadrilateral is a parallelogram, the diagonals bisect each other. Here, the given part is that the quadrilateral is a parallelogram, and naturally, the proved part is that the diagonals bisect each other. So, on switching them, we get the converse of this theorem, which can be written as if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. Okay, how do we prove this one? Well, let us first have a quadrilateral ABCD where the diagonals AC and BD bisect each other at O. We can say that OA is equal to OC and OB is equal to OD. So, in triangles AOB and COD, it's already given that OA is equal to OC and OB is equal to OD, and angle AOB is equal to angle COD because they are vertically opposite angles. So, side, angle, side. Thus, triangles AOB and COD are congruent by the SAS criterion. Now, in these congruent triangles, let's just name these angles 1, 2, 3 and 4. So, it's evident that angle 1 is equal to angle 3 and angle 2 is equal to angle 4 because they are just corresponding parts of congruent triangles. Now, focus on these two opposite sides and this diagonal between them. Doesn't this remind you of a pair of parallel lines and a transversal? Seems quite similar, doesn't it? Now, you remember we have studied a theorem in our previous classes which taught us that if two lines are cut by a transversal and the alternate interior angles are equal, then the lines are parallel. Now, if you think about it, here angles 1 and 3 form a pair of alternate interior angles. And we have already proved that they are equal. So, following this theorem, we can say that in this quadrilateral, sides AB and CD are parallel to each other. Now, if you think about it, the exact same steps can be used to prove that these two sides AD and BC are also parallel. We can prove that these two triangles AOD and COB are congruent by the same SAS criterion. Now, this implies that these two angles, say 5 and 7, are equal, and so are these other two angles 6 and 8 because they are just pairs of corresponding parts of congruent triangles. Now, We look at these two sides AD and BC and choose a diagonal of our choice, say BD. It's pretty evident that these two angles form a pair of alternate interior angles, and we have just proved that they are equal. So, by the theorem we used a while earlier, these two sides AD and BC are also parallel. So finally, we have a quadrilateral where both pairs of opposite sides are parallel. Fits the definition of a parallelogram perfectly. It's easy to see then that quadrilateral ABCD is indeed a parallelogram. See, we just proved that if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. Was that difficult at all? Considering all that we have covered in this chapter, this was probably a cakewalk. So far, we have covered 4 important properties inherent to each and every parallelogram, and proving their converses taught us that if in a quadrilateral any one of these conditions is satisfied, then it is a parallelogram. Now, there's another condition which is actually the least required condition for a quadrilateral to be a parallelogram. It is stated in the form of a theorem as a quadrilateral is a parallelogram if a pair of opposite sides is equal and parallel. Visualizing this theorem, if there's a quadrilateral, say ABCD, where a pair of opposite sides, say AD and BC, are equal and parallel, then ABCD is a parallelogram. So how do we prove this one? By utilizing the information we have already been given. Simple enough, isn't it? So, considering triangles ABD and CDB, AD is equal to CB, it's already given, and these angles, say 1 and 3, are equal because they form a pair of alternate interior angles. And DB is equal to BD because it's common in both the triangles. So, side, angle, side. Thus, triangles ABD and CDB are congruent by SAS criterion. Now, in these congruent triangles, let's name these angles 2 and 4. So, we can say that angle 2 is equal to angle 4 because they are corresponding parts of congruent triangles. Now, if you look closely, you will be able to see that this diagonal actually acts as a transversal between these two sides. And these two angles form a pair of alternate interior angles. Now, we recalled a theorem a while earlier which reminded us that if two lines are cut by a transversal and the alternate interior angles are equal, then the lines are parallel. We have already proved that angle 2 is equal to angle 4. So, following this theorem, we can say that these two sides AB and CD are also parallel. So basically, in this quadrilateral ABCD, the two pairs of opposite sides are parallel, which means ABCD is a parallelogram. That was pretty amazing, wasn't it? We now know 5 different ways of identifying a parallelogram. The foremost condition is something that goes without saying, that the shape must be a quadrilateral. Now, if in this quadrilateral, each of the diagonals divides it into two congruent triangles, or the opposite sides are equal, or the opposite angles are equal, or the diagonals bisect each other, or a pair of opposite sides is equal and parallel, without even a second look, we can say that this quadrilateral is a parallelogram. By now, we have a pretty good idea of the different properties inherent to all parallelograms. But we haven't really applied them extensively, so we don't know what the possibilities are. Don't you worry though, in the coming videos, we would be catering to just that. Excited? Watch this quick summary and rush to the next one. So, in this video, we explored a new property and even a new condition for a quadrilateral to be a parallelogram. We proved that the diagonals of a parallelogram bisect each other. We also proved the converse, which states that if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. And a quadrilateral is a parallelogram if a pair of its opposite sides is equal and parallel.